In this tutorial, we'll be exploring the idea of triple integrals. In calculus, we use integrals to find areas under curves and volumes under surfaces. When dealing with three-dimensional regions, we extend this idea to triple integrals. A triple integral allows us to sum up values over a three-dimensional region, as shown on the slide. Here, f of x, y, and z represents a function of three variables, and dv represents a tiny volume element which we sum over a specified region R in 3D space. To integrate over a 3D region, we need to break it down into infinitely small volume elements. The most common way is d equals dx times dy times dz, which represents a tiny rectangular box in Cartesian coordinates, as can be seen in the next slide. dv can be seen as a tiny rectangular element of this giant solid in three-dimensional space. Now let us solve a problem to understand triple integrals a bit more better. The solution is pretty similar to how you would solve a simple integral, but you do it thrice across three variables. For this particular question, you have to find the triple integral from 0 to 1 for dx, dy, dz. First, we integrate with respect to x, and we have the integral of 1 time dx is x, and expanding that you get 1 minus 0 dy dz. You again wind up with that. Integral of 0 to 1 dy is again y from 0 to 1 dz. You have 1 minus 0 dz. That gives you that. And then finally you have integral from 0 to 1 dz, and that gives you z 0 to 1, 1 minus 0, 1. So your final answer for the triple integral is 1. The previous example is just a very simple application or problem of triple integrals. Triple integrals can be used for many other things, not just volume calculations. A list of applications can be seen on the screen. It is used for finding mass when density is given. It can be used to compute centers of mass in physics. It's also used in fluid dynamics. It can be used to model heat distribution, determine electrostatic potential, and to study population density distributions in environmental and social sciences.